Well, we're into the next big block of reactions involving the benzene ring. We've looked in the last 3 videos at alcohols, ethers, and epoxides, and how they'll react in acid conditions, and epoxides, how they can react in acid or base conditions. But we're going to move now to the benzene ring. The benzene ring, of course, is aromatic, so it's going to take a little bit more oomph. We're going to have to add a little more reactivity to the reagents that are going to react with the benzene ring. So in the first 3 videos of 5, this being the 12th video, we have 5 videos to watch on benzene's chemistry, whether it be electrophilic aromatic substitution, where we attack an electrophile, something that's positive or partially positive. And we're going to often use a catalyst because we're going to have to break aromaticity for a little bit of the time during the intermediates, the formation of intermediates before we go to product. We'll have to have some high energy intermediates, so we'll have to use a catalyst. That's going to be 4 videos. In the last video, we're going to discuss nucleophilic aromatic substitution. We're going to flip things, where in the first 4 we'll look at electrophiles being attacked, 5 different types of electrophiles being attacked. But in the last video, we'll flip things so that we have a nucleophile, a fairly strong nucleophile in most cases, attacking the benzene ring. So the arrow going the other way. So let's look at just the basics of electrophilic aromatic substitution, and then we'll look at 3 types of specific types of electrophiles. So let's go ahead and look at, if we can, just electrophilic aromatic substitution, where we're going to have strong Lewis acid or Bronsted acid conditions. What we're going to do for this first video is just look at the first 3 here, nitration, sulfonation, halogenation. We'll look at alkylation and acylation, the last of 5 types of electrophilic aromatic substitution reactions, in the next video. So we're just going to look at halogenation, nitration, and sulfonation. But we want to make sure we understand there's a trend, or a pattern, I should say, for any of these types of electrophilic aromatic substitutions. That is this. We have the benzene ring that attacks an electrophile, again, either full or partial positive. And we make what's known as a sigma complex, or a cyclohexadienyl cation, very high energy intermediate. It's non-aromatic, has a full positive charge. And what it's going to take to come down in energy is some weak base to take a proton. This is going to be the second step, or last step, we should say, for any electrophilic aromatic substitution. The last step is always going to be a weak base, something in solution, whether it be water, sulfate anion, whatever, that takes the proton off the carbon in the sigma complex that is sp3 hybridized, so that the electrons can, it should be right to this middle portion, bounce back to a pi bond and reestablish aromaticity, where in the end we've taken the H off this position and replaced it with an E. So indeed it is electrophilic aromatic substitution, where the electrophile has been attacked and we've substituted the hydrogen with that electrophile. So that's the pattern. I'm going to just talk about it just a little bit more in the next slide. And in later videos, we'll look at substituent effects. Y being something other than a hydrogen, how would that affect the reaction? Well, if we had 2 substituents on the ring, how would that affect this reaction? How can we put 2 substituents on the benzene ring? That would be a multi-step reaction, where we're trying to start with benzene and put a Y and a Z on the benzene ring. And then we'll finish, as we said, with nucleophilic aromatic substitution, where we flip everything. I want to point out that if we flip everything as far as the type of reagent added to benzene, terms like activator and deactivator have to change in terms of their context. Activators and deactivators are like terms we use in society, such as beautiful. That needs context, because it depends on what century you're living in as to what defines beauty. So terms like activator and deactivator need context. So for electrophilic aromatic substitution, activators and deactivators might be very different from activators and deactivators for nucleophilic aromatic substitution. Let me just give you an example. If we want to attack an electrophile with the benzene ring, we want Y to donate electron density so that it can be an activator. But if we flip things and we have some Y group on the benzene ring and we have some leaving group, we'll say a chlorine, and we want to attack the benzene ring, we don't want a donating group. We want Y to be a withdrawing group. So a withdrawing group for NAS, would be an activator. But a withdrawing group for an EAS would be a deactivator. Alright, so now that you're thoroughly confused, it's safer just to say, what is it doing to the ring? Don't use terms like context, use terms like white, tan. That man is white. We could say Y is a donating group. A donating group would be a good thing for attack of an electrophile with the benzene ring, but a donating group would be a bad thing if we're trying to attack with a nucleophile some partial positive carbon. A donating group would be bad. Donating group would be good for EAS. Donating group would be bad for NAS, nucleophilic aromatic substitution. Alright, so that's just giving us a little bit of a context for terms like activator and deactivator. So from here until the 5th video, activators are donating because we're in the context of an EAS. Activators are donating groups. Alright, let's go back to just the basics. We have a benzene ring. Well, we have nothing on it but just hydrogens. Well, we can attack an electrophile. Typically we'll need a catalyst, something added to make this more reactive. We'll attack the electrophile using those 2 pi electrons, put it on any of the carbons, it doesn't matter, we'll just use the 12 o'clock position, and the carbon that is in the cold now because it lost sharing of those 2 electrons is next to that position that has the electrophile, not here but next to. It's still sp2, this one is sp3, and we said in the first 5 minutes here that the weak base has to come in and attack the proton on the carbon that is sp3 hybridized so that we can establish or re-establish aromaticity. So arrow going out to the electrophile in the first step, weak base coming in to grab the proton off the carbon that is sp3 hybridized, and the sigma electrons falling back to a pi bond, and in the end we have our electrophilic aromatic substitution. Because we temporarily break aromaticity, we need to use very reactive electrophiles, and we do that by adding sometimes, in most cases, a catalyst. Not always. First step is the rate limiting step because we're going from aromatic to non-aromatic. Thus we must consider the most stable sigma complex or cyclohexyldienyl cation. Alright. Let's go ahead and just summarize the 5 different types of electrophiles we'll see in EAS reactions. EAS, again, electrophilic aromatic substitution. So let's identify what the electrophiles are going to be in the 5 reactions that we'll consider. So Br2, I2, often used for, Br2 and Cl2, often used for halogenation. It's usually Br2 and Cl2 used with some sort of Lewis acid, iron trichloride, aluminum trichloride, and what we typically consider as the, I'll just use chlorine as an example, we consider a sigma complex formed between the dihalide, or the halogen in the diatomic form, Br2 or Cl2, reacting with the Lewis acid to make either a salt or what we'll see as something close to this. We'll treat it as if it goes to a salt. And this is odd because the chlorine has a full positive charge if it's in the salt form. Now it's often the case that we're not in a true salt form. We're something in between, a sort of sigma complex, something close to this structure. But I'm drawing this because I think it'll help us practically get to the right product, because now we can clearly see our electrophile is not X plus. We'll just use chlorine as an example here, but Cl plus. We could also have done the same thing with bromine and AlBr3. What about using nitric acid and sulfuric acid? Now, I'm not going to draw the full salt, but for this, we're going to see that what we have is what's called the nitronium ion. That if we take nitric acid, which is going to be our electrophile provider, and sulfuric acid, which is going to be our catalyst, we can make the nitronium ion. So that's going to be the key electrophile generated when the catalyst is added to nitric acid. Now I'm going to do something here that kind of continuing on theme. The protonated form of sulfur trioxide. Sulfur trioxide is electrophilic, but we'll consider the catalyst effect, sulfuric acid, and how it can donate a proton to one of those three oxygens to make this fully positive, make this a little more reactive. So we'll consider our protonated sulfur trioxide as our electrophile when we have a mixture of sulfur trioxide and sulfuric acid, also known as fuming sulfuric acid. Our last two, and again we're going to just cover these three in this video as in specifics, but we'll get to the alkylation acylation reactions in the next video. So alkylation, where this is just an alkyl halide, we can have, I should have used AlX3 since we can have Br3 or Cl3. We can have the X ripped off, just like we did here. We ripped off one of the X and left the other one with a positive charge. We can rip off the X here, giving the electrons to the aluminum, a Lewis acid, and leaving ourselves with an R plus AlX4 anion. So we rip off the X, and we're going to do the same thing here. It's called an acylium cation. This is an alkyl cation. So you want to get good, and again I'm going to change that just to X3. So AlX4. So alkyl cation, acylium cation. We're not going to consider rearrangement for this one, but we will for this one. So I wanted to go ahead and before we get into the details of all these 5 electrophilic aromatic substitution reactions, it's probably good just to remember what electrophile is generated in these solutions of reagent with Lewis or Bronsted acid. So in all cases, we find the electrophilic site. We need to identify what that is and attack it with 2 pi electrons from benzene. So the 2 pi electrons from benzene could attack Cl plus or Br plus. 2 pi electrons could attack the nitronium ion, and so on. So let's look at these 3 and we'll be done. Well, first of all, halogenation of benzene will not occur just by adding Br2, much like what we can do with dienes. We can have, in the case of a diene, where we don't have aromaticity, we can have what's called the 1,2 addition of bromine across the pi bond where the pi electrons attack, and then the other bromine comes in and finishes the reaction. We can have that attack start this way. Or we can have the 1,4 addition where we make the same bromonium ion and we have the second step, the bromine attack at a conjugate position. So we can have these addition reactions because we're really not breaking aromaticity, so there's no hindrance to addition. But if we try to have an addition reaction with benzene where we just add 2 bromines across the pi bond, like we did here, 2 bromines across the pi bond, there's no such reaction because, of course, if we break the pi bonds and make sigma bonds, these carbons right here and here are sp3 hybridized, and this would not be aromatic. So we don't get additions of halogens to pi bonds like we did with alkenes and dienes. With benzene rings, we have to have substitution. Substitution gives us a lower energy aromatic ring back. So we still attack, we make what we said is a sigma complex, and the positive charge here is not going to be directly satisfied. We're not going to have another bromine come in and attack this like we did up here in these addition reactions. No, that would give us a high energy addition product. What we have to have happen is the bromide left, or the AlBr4 minus, comes in and attacks the proton at the sp3 carbon. It attacks the acidic protons, not the electrophilic carbon, to reestablish aromaticity. Now I've drawn the pi bond in a different place. It doesn't matter. 3 pi bonds in this 6 carbon ring is the benzene ring. So we reestablish aromaticity by having, instead of bromide come in and act as a nucleophile, it has to come in and act as a base. So remember that. Let's go ahead into the next slide and start remembering that in the second step and the last step, we have to have action as a base. So let's draw the mechanism out. So I'm going to take benzene, and we can't just add again Br2. We can't do that because it's not reactive enough. We have to add some sort of Lewis acid or even a Bronsted acid. You can use iron in Br2, and that will make FeBr3, or just add this directly. And what we're going to have if we have Br2 and FeBr3 is either the, acid-base complex, where we don't have a full breaking of this bond, or the salt, depending upon solution. We're going to have this acid-base complex where the bromine, Br2, has started to poke its electrons into that iron core and create a very electrophilic bromine that pulls on the electrons from this bromine to make this a very reactive, partially positive bromine. Let's just consider the salt, though, because if we do that, pragmatically, it just helps us see how to attack Br2. So I'm going to go ahead and draw this. If you're ever given Br2 and FeBr3, I recommend that you just right above it or below it say, this really just gives me bromine, one of them attached to this iron, FeBr4 minus, and the other bromine with a positive charge. Now again, it may not be in a full salt form, but it just helps. So we can know, okay, now I can attack clearly what is the electrophile. I can attach that bromine to the, we'll just use the 12 o'clock position. Where does the positive charge go? Again, if we're using the pi electrons and we attach the bromine here, the positive charge goes to the other carbon. So that's our sigma complex, our high energy, non-aromatic sigma complex that has 3 resonance forms. We can delocalize the positive charge from here to here and from here to here. So again, resonance is important to consider as we consider electrophilic aromatic substitution. Now, how do we finish it? Well, we don't have water present. You can't have water present with these Lewis acids. But we have FeBr4 minus. What we're going to do is treat this as a weak base. This weak base is coming in and acting as a base. We're not going to put this bromide on the carbon. That would give us addition. We're going to attack the acidic proton in this very acidic sigma complex and reestablish aromaticity, generate HBr, because we're going to have that bromine come off as it, and guess what? We regenerate our catalyst. So it is indeed a true catalyst, since we take one of the bromines in FeBr4 minus, bond it to the hydrogen, and we can maybe get that to bubble off as gas, and we reform our catalyst, FeBr3. Now this is just a particular mechanism that fits the pattern that we've seen previously, wherein we break the benzene ring's aromaticity with some attack of an electrophile and then tear off the proton. This is just a particular electrophile, Br+, and this is just a particular weak base, FeBr4 minus, that we're using. So you want to start seeing the pattern, up in energy and down in energy. And I'm just drawing the salt form of this Br2 with FeBr3. That's our first one, halogenation of benzene. Using either Br2 or Cl2 can be used with FeBr3 or FeCl3. Alright, let's go ahead and look at the next one, nitration of benzene. When we hear nitration of benzene, we want to think nitronium ion. That was what he said is the electrophile. Let's see how that's made. This is acting of all things, as a base. This nitric acid is going to pick up a proton from sulfuric acid. It's the weaker acid, so we're going to force this to act as a base on the left, and the sulfuric acid gets to be the acid. It's kind of an odd thing to have two acids reacting with each other. Well, if they react with each other, somebody has to act as the base. So if nitric acid does that and picks up water, we can have loss, or it picks up a proton, we can have loss of that water to make the nitronium ion. So what I'm going to do is just propose that we start, if we have a mixture of nitric acid, that's our reagent, and we add a catalytic amount of sulfuric acid, and typically a little bit more than that's fine, we can say, hey, that just gives me, without too much mechanistic detail, I'm just going to say, that gives me my electrophile. Now I'll start talking about the mechanism. I attack the nitrogen, in nitrogen, I guess, nitronium ion, and that pi bond gets advanced up. So I'm going to go ahead and draw out the full structure for the nitronium ion. So we would have a negative charge on this oxygen, because we had to advance pi electrons up, because nitrogen can only have 4 bonds off of it. So we attack the nitrogen, and the other pi bond to the other oxygen is intact. But of course we would have a positive charge on the nitrogen, because we have 4 bonds on that nitrogen. Just replaced a pi bond with the sigma bond. We replaced, as we attacked the nitrogen, we took one of the pi bonds up to the oxygen to make room, and we replaced it with a sigma bond to that nitrogen. Alright, so where's the positive charge in the sigma complex? Because we used the pi electrons to attack the nitrogen in the nitronium ion. Well, that's right, next to where the electrophile is bonded. What do we do in the last step? Well, our weak base, we're going to just use water. Doesn't really matter. You could have used the conjugate base of sulfuric acid. It doesn't matter. We just have something in this solution, this aqueous typically solution of acids, that has to act as a weak base. So you may see different types of weak bases used. Conjugates of the acid or water has to come in and act as a base. What do? Go after the proton, connect it to the sp3 carbon so that we can reestablish aromaticity. And we have nitration of the benzene ring. This is just, again, a particular mechanism that fits the pattern seen previously. It's not necessarily on page 2, but it's just a new electrophile. And our weak base is just something in solution, whether, again, it's water or sulfate anion or hydrogen sulfate anion. The point is we reestablish the acidic proton so that it can go back and do the same thing. We do not lose acidity in this solution. By tearing off that proton, we make H3O+, which is just a form of that acid on water, so it can go back and do the same thing. We can have the reaction of that acid generate nitronium ion, and we can go round and round. Your pH of this solution never changes. Alright, last one, and we'll finish with this. Sulfonation of benzene. Fuming sulfuric acid, this is going to act as our base here. Fuming sulfuric acid has sulfur trioxide, SO3, used with acid. They call it fuming sulfuric acid. Now, it's not necessarily the case that we have to draw this protonated, but if we're in acid conditions, it's very likely there's some hydrogen bonding with sulfur trioxide to give it a little more reactivity as an electrophile. So we're going to protonate this oxygen, give it a little bit more electrophilicity for this benzene ring to attack. Now this mechanism has already been shown. We're going to attack that protonated HSO3, or the protonated sulfur trioxide, which we said is the electrophile in fuming sulfuric acid. We can advance the electrons up so that we have a negative charge on the oxygen as we attack the sulfur, just like we did with the nitronium ion. And we can have sulfate or hydrogen sulfate or water come in, attack that proton as a weak base, reestablish aromaticity, and again we get our catalyst back, or our sulfuric acid or our acidic proton back, whether it be H3O+ or whether it be in this form, we're getting a catalytic proton back. So this is truly acid catalyzed. So this is just our sulfonation of benzene using fuming sulfuric acid. Now a very similar reaction is seen when SO3 is not present. We can also have a protonated form of sulfur trioxide formed with just sulfuric acid. I'm going to skip that for sake of time for this video, but you can see if we take sulfur trioxide and have it react with itself, we can have, just like we did with nitric acid, if we take sulfuric acid here and have sulfuric acid react with itself, it can generate, after loss of water, it can generate a protonated form of sulfur trioxide, or the sulfonium ion. Let's go ahead and finish, just in summary, what we've covered. We've covered halogenation, nitration, and sulfonation. Halogenation, our electrophile was X plus, Fe or Al, X4 minus. Nitration, we had a nitronium ion generated by sulfuric acid and nitric acid. And sulfonation, we consider the sulfonium ion generated in fuming sulfuric acid or just sulfuric acid by itself. No SO3 added. And we know what we formed. Just please know that you have substitution with those electrophiles that we've identified. You have substitution of a proton. Again, if X2, we usually use Cl2 and Br2 for halogenation. And we can use fuming sulfuric acid or just concentrated sulfuric acid to make our sulfonation product. Alright, those are the three that we wanted to cover in our first video on EAS. We'll look at two more, alkylation and acylation, in the next video. Something to consider, can this reaction happen twice? In other words, could this ring, now sulfonated or nitrated or halogenated, could it be more reactive with the reagents than the starting benzene rings? In other words, once monosubstitution occurs, is the ring here more reactive towards a second EAS reaction, or is it less reactive? Let's finish this thought. Halogens, are they donating to the ring or withdrawing? Donating, they would activate the ring. If they're withdrawing, they would deactivate the ring, and this would be more reactive than the halogenated ring. Hope you're saying that this is a withdrawing group. This withdraws. It does withdrawing more by inductive effect. Nitronium ion, oh, this is certainly electron withdrawing, both by inductive effect and resonance effect. We'll see that in not the next slide, but the third one. We'll see substituent effects, that nitro groups are very electron withdrawing. They're one of the strongest electron withdrawing groups you can have. In the same way, this sulfonic acid group is also going to be a very electron withdrawing group. So these would all be deactivated. Why? Because the group we put on is withdrawing. Withdrawing means electrons are removed from the ring and it can't attack electrophiles as easily. So withdrawing in the context of electrophilic substitution reactions are deactivating groups. Not shutting it off, but just deactivating it, making it less reactive. Well, that's it. We'll look at the alkylation and acylation reactions in the next video. Bye-bye.